All right, section 1.4 is titled Continuity and One-Sided Limits. We will talk about continuity first. I've even mentioned this today when we were talking in lesson 1.3, the word continuity. So we have this general feel for what continuity is, and we usually describe it something like this. I can draw it and I don't have to pick up my pencil. Right? Well, if I could draw it and I don't have to pick up my pencil, that's continuous. That's not a very precise definition, so we need a better one than that. But that's the general feel for what it means for something to be continuous. So we've got two different types of continuity. We're going to first look at continuity at a point. So it just means at a specific location is it continuous. So this says that a function f is continuous at a specific point c as long as the following are true. The first one, f of c is defined. Right? There's not a hole. There's not an asymptote. We don't have any jump in the graph kind of thing with holes on the both ends. It's defined. The second one is that the limit exists. So what does the limit exists mean? Well, it means you can get infinitely close on the left and on the right. And in particular, this means there's not a jump at that location. Okay, you cannot have a jump. So the first one is eliminating the possibility of holes. So there's no hole at that point. So there's no hole at C. There might be a hole somewhere else, but there's not one at C. And there's no asymptote at C. So that's the first one. That eliminates that possibility. The second one eliminates the possibility of a jump. So there's no jump at C. And hopefully you're looking at those and you're saying, right, because if I had a jump, or if I had a hole, or if I had an asymptote, I'd have to pick up my pencil, right? Yeah. So at that particular point, that can't happen. The last one actually says that the limit value has to equal the function value. And you might be thinking, well, doesn't that always happen? And there are cases, at least the way that they're defined, where that does happen, that this gets, is failed. So imagine if you had this going on. It doesn't even have to be like changing like spaces or whatever. It can be just continuing on. Let me do it like this, actually. Okay. So there's a hole there, but it's got a dot somewhere else, like right there. Pretend like they're lining up. Well, if you do this, technically both conditions 1 and 2 are satisfied. Not the descriptors I've written to the sides necessarily, but the first two details here are satisfied. It's defined, like this is C. This is at a C value. It's defined. The value is this open or this filled in dot right here. The limit exists, right? I can get infinitely close to the open dot. There's no problem with that. So that's the second condition. But it fails condition number 3 because the definition of the value, the filled in dot, is not the same as the limit value, which is the open dot. So this is what's being eliminated. In some sense, it's also eliminated as a jump. Both of these are eliminating jumps, the way that they're describing. The first one's just eliminating jumps that look more like this. Right? A jump more like that. Whereas this is also kind of a jump, but not exactly what we usually mean when we say jump, right? Yeah. So these are the things that can't happen. And you should be saying, well, yeah, because I'd have to pick up my pencil, like I mentioned before. Now, this is continuity at a specific point. And so then what we're going to do is we're going to generalize it to being over an interval. So on an open interval, a function is continuous when it's continuous at every point in the interval. That seems quite reasonable. If it's continuous at every single point between A and B, it should be continuous on the interval from A to B. And if it's continuous on the entire number line, right, from negative infinity to infinity, we say that it's everywhere continuous. And usually we just say it's continuous, and we don't even clarify the everywhere part. So you usually see the clarification only when it's necessary, and when it's not necessary, you don't clarify it at all. That's typically what is described. Okay, we're going to do the first two, and then we'll call it good for today, because I think that'll get us plenty enough far that we'll be able to finish comfortably on Wednesday. The first one and the second one actually the third one as well, all have one-sided limits. Okay, so we haven't talked about one-sided limits too much yet. We defined them. We defined them in section 2, I think. So it's talking about coming from a specific direction. So over here, this one says 8 positive. What does 8 positive mean? It says the limit as x approaches 8 positive. From the right. So this means from the right. I think it's been a week since we looked at that definition. From the right, or you can think of it from being the positive side. The part that sometimes confuses people is the direction in which we're moving, but the positive is actually telling where we're coming from, right? Think of it as your hometown, right? Where did you come from? That's what this positive is indicating. Where am I coming from? So 8 positive. Now, the reality is that coming from 8 positive or coming from 8 negative may or may not matter. Just like when we were working in the last section where it just said limit as x approaches 8, and we took the 8 and we plugged it in, if we can do that here, we do that here as well. Okay? So can I put the 8 in? Yeah, I can. There's no problem with that. So I've got 1 over 8 plus 8. We're good to go. This is 1/16. And so the question says find the limit, right? The directions originally, find the limit if it exists. Well, we found the limit, so therefore it exists. You with me? It sort of feels like counterintuitive. It feels like you should have established that it existed first, but it doesn't really work that way. You really just attempt to find it, and if you're successful, then it existed. If you're unsuccessful, you've got to go a little further and figure out why and what's going on, or is there another technique I needed to use? So this one exists, right? It exists, and this is the value. It's 1/16. The next one should look familiar. It's similar to something we ended with last time. Has radicals, right? Yeah.
Explaining why, and what do you want to see?
Thank you. So on this one, this is exists. It's if it does not. Sorry, clarify. Do you see that says? If it does not explain why. So we haven't gotten one to it does not yet. So when we get to the it does not, we would explain why. So if it does not, what we would say though, just to answer your question, Max, is we would say something like, there's a hole in the graph, right? So the ones we saw in the last section where they canceled like an x minus 4 on the top and the bottom canceled out, when that happens, it creates a hole in the graph. And that's what we would say. Why explain why not? Because there's a hole in the graph there. If you don't have the ability to plug it in at all, like on this one, let's say it said x approaches -8. I don't care if it says plus or minus. If it approaches -8, the limit doesn't exist. And it won't because there's going to be an asymptote there. How do I know? Because I don't have a 0 on the top, but I still have a 0 on the bottom. And so then we would describe it from that way. If the limit doesn't exist, we would explain why. Oh, there's an asymptote at -8. That's what we'd be looking for. Yeah. But if it does exist, it's proven already because we found it. Yeah. Okay. Again, we're going to attempt, just like in the last section, regardless of if it's a one-sided limit or if it's a two-sided limit, to simply put the number, in this case 9, in. Not -9, it's 9 from the negative side, but it's 9. What happens if I try to put in 9 here? I get a 0 on the bottom and on the top, okay? Now, if it was just 0 on the bottom, we would be done, and we would say the limit doesn't exist and there's an asymptote. Everybody clear on that? But the 0 on the top and the bottom, it means that there's some way that we can simplify. Yeah?
Could we not also make the square root of 9 -3?
Okay, so that's a good question. So when you have a square root in a problem given to you like this, that square root is a principal square root. A principal square root means it takes on the positive value automatically.
Okay.
Yes. So the only time we put pluses or minuses, like you're thinking about like when you solve, actually is when we usually do that, is when you insert a radical into an equation that didn't already have one. So think about when you solve things like, for example, x squared equals 25. So if the problem starts out like this and you insert the square root to do the solving, that's when you end up putting the plus or the minus in there. But if the square root's already there, it's the principal square root and it's the positive part only. Yeah, thank you for asking that. Good clarification question. Okay, so we got 0 over 0. What did we do last class period when we ended up with 0 over 0 and there were radicals involved? We multiplied with it's the numerator. The conjugate is what we called it, yeah. So, and what we're doing is we're doing something called rationalizing. So we're rationalizing, we're trying to get rid of the radical. And specifically, our radical's in the numerator here, so that's where we're trying to get rid of it. It doesn't matter if it's in the numerator or the denominator, the process is the same. You do it for the denominator in a lot of other classes. Here we seem to do it with the numerator more, but it could have just been flipped upside down and we'd still be doing the same thing, okay? So what is the conjugate of the square root of x minus 3? Right. And just like way back when you learned all about fractions and so forth and adding and subtracting, whatever's to the top has to be done to the bottom for multiplication, right? In the denominator, you don't really want to distribute anything. You just want to leave it kind of in these pieces that they're already in. So we need to write limit again. Keep that in mind. If you haven't written the limit again, squeeze it in there. The limit as x approaches 9 from the left. And in the denominator, I now have x minus 9. And I have the square root of x plus 3, written just like that. The numerator, however, I want to clean up. I mean, that's the whole point of why I chose those particular values. And if you'll remember, we talked about it last time, but the reason we choose conjugates is because the inner and the outer terms will be identical, except for the sign. One's positive and one's negative. And when you add two things together that are identical with opposite signs, you get 0. Okay? So the inner and the outer terms just won't be there. So what that means is that this question's numerator reduces to multiplying the first terms together. What is square root of x times square root of x? X. And then the last terms together. What is negative 3 times positive 3? Negative 9. And lo and behold, what showed up? X minus 9, which is also in the denominator, right? This is what happens when we rationalize. Pieces show up that match from numerator to denominator that we're able to reduce. It's kind of like when we have the factoring available to us, right? When there's something that's able to be factored, there's going to be a piece on top and a piece on bottom that have the same factor. Sometimes that can help you in identifying what might be the factors I'm looking for. I definitely know how to factor the top. The denominator, maybe not so much, but you kind of have a clue into it. So this piece and this piece cancel. So again, that step's everything written down right now should be written when you're working the problem out. I will be looking for it, okay? This next piece right here, if you don't want to write it, that's okay. It's just a little bit of a cleanup step, identifying the pieces that remain. What remains on top is what? A 1, good. And then on the denominator, I have the square root of x and the plus 3. Okay, that's your optional. So whether you're doing it from this point or whether you're doing it from the step before, we now have the ability to attempt again to plug in the number 9, right? We're ignoring the negative for the most case. The negative really will help us to indicate what's happening otherwise on the limit parts, which we'll talk about another one next time that has that, but this one doesn't. So if I put the number 9 in now, what's the square root of 9? 3. And I get a total of 1/6. Okay, everybody good? All right, we're going to pause it there. Number 3 is quite different. I think it's a good place for us to pick up next time. These have been very much like the things we did in the previous section.